Let us start our new chapter. And today I am going to discuss the chapter Magnetism and Matter. When you hear this name itself, you know a lot of ideas regarding this chapter. You have seen a magnet and you have studied about magnets in lower classes. Like if you just suspend a magnet, it will always align in the north to south direction. Like poles of a magnet repel each other. Unlike poles of a magnet attract each other. All such things are familiar to you already. Now in this class, actually as per the new syllabus, only a little is there in this chapter. So we will try to complete everything as early as we can, so that we will shift our attention to the next chapter, which is nothing but electromagnetic induction. So we will start our discussion of this chapter with the topic properties of magnetic field lines. Okay, so I got the properties of magnetic field lines. The first property, as you can see, the magnetic field lines of a magnet or a solenoid form continuous closed loops. They form a continuous closed loops, which means this is unlike the electric dipole, where the field lines began from a positive charge and end on the negative charge or escape to infinity. We have told while discussing electrostatics that electrostatic field lines never form closed loops. Electrostatic field lines never form closed loops. What is it says? Magnetic field lines always form closed loops. Some examples that we know. This is a current carrying conductor. Around a current carrying conductor, the magnetic field lines are concentric circles that we have seen in our class. They are concentric circles. Now my question, can this represent? This is actually a question from one of the examples, let me tell you, that I am going to discuss later. This cannot be a magnetic field line. This cannot be a magnetic field line. Can this be a magnet? This is a solenoid, and this also cannot be a magnetic field line. As you can see, as I already told in the previous chapter. So the field lines of a solenoid should be something like this. That is, it has to be a part of a closed loop. The field lines have to be a part of a closed loop. Now the question comes, can this be a magnetic field line? Yes, exactly. Because you can see that this forms a part of a closed loop and this is actually closed loop. So let me tell you, this may represent magnetic field lines. So the most important property that we have learned regarding a magnetic field line is that it always forms closed loops. Moving on to the second property. The tangent to the field lines at a given point represents the direction of the net magnetic field at that point. See here, this is a bar magnet. This is a north pole, this is a south pole. And I am saying outside a magnet. Or it's a general misconception to say that magnetic field lines originate from north pole and they terminate in south pole. It's a big blunder, because magnetic field line has no end points. They never originate, they never terminate, because they always form a closed loop. My question, if I ask you the question, which is the initial point of a circle? Which is the final point of a circle? Answer is, a circle has no initial point, neither final point. Which means, just like this one, so what I am coming to say is that magnetic field lines never originate from north pole, never terminate in south pole, but we can say likewise, outside a bar magnet, field lines are from north pole to south pole. Inside a bar magnet, it is from south pole to north pole. You can see here. This is the direction of the magnetic field inside the magnet. Now I am going to draw a tangent. At this point, the tangent is drawn likewise, and the tangent drawn will give the direction of magnetic field at that point. So now looking at a point here, this is the direction of the magnetic field. Just like we have seen with an electric dipole, the magnetic field lines along the axial line is parallel to the magnetic dipole moment. Magnetic dipole moment is from south pole to north pole. I just said only because it is not there in our syllabus at present. So tangent the field lines at a given point represent the direction of the net magnetic field at that point. So this is an important point. Now here, if I draw a tangent, this is the direction of the tangent here. Take another point, this is the direction of the tangent. So these are the directions of magnetic field lines, I have to say. Now coming on to the very important property, which is magnetic field lines do not intersect. Do not intersect. Magnetic field lines are never going to intersect. For if they ditch, the direction of the magnetic field would not be unique at the point of intersection. I told you in the previous property that the magnetic field lines, the tangent drawn to the magnetic field lines at a given point represent the direction of magnetic field at that point. Suppose that this is one magnetic field line, this is another magnetic field line. So if you look at this point, I can draw one tangent likewise, I can draw another tangent likewise. Both represent the same magnetic field. Both representing the same magnetic field, it is impossible. Because magnetic field has a fixed value, or magnetic field is fixed at a particular point. It's a vector. Understand that the magnetic field is a vector quantity. A vector is unique means it has a fixed magnitude, it has a fixed direction. So in this case, it does not satisfy that condition. So let me tell you clearly that the magnetic field lines do not intersect as do electrostatic field lines. So let me tell you, this cannot represent electrostatic field line, this cannot represent magnetostatic field lines. So that is one important point I can say. Now, then what will be the shape of the magnetic field lines? Okay, this can be a magnetic field line. 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 So if you look at these lines, they are never going to intersect, right? They are never going to intersect. So they may represent the magnetic field lines, I would say. Now my question, if I ask you the question, I am taking 2 points A and B. My question is, where will be the strength of the field maximum? Which field will be greater here? I will say BA. I am giving you 4 options. Option 1 or 2 options. I am saying BA less than BB. Option 2, BA greater than BB. What is probably your answer for this question? Where will be the strength of the field is greater? Let me tell you, it's a very simple question. Answer is in 1. Why? The magnetic field at a particular point is represented by, or the strength of the field is denoted by the relative number of magnetic field lines intersected by a certain area. Now, if I consider a particular cross section here, and if I take a similar amount of cross section, say I don't know whether I am going to work it out. Yeah, fine, it's working well for me. If I consider a similar cross section, what is the inference? You can see that here the relative number of field lines intercepted is 1. Here the relative number of field lines intercepted by the same field is 3, or same cross section is 3. Which means the strength of the field at a particular point is determined by the relative number of magnetic field lines intercepted by an area. Just like all other properties, I can say, see here, so understand that it's a part of a curve only. So the ripple laterally, that is perpendicular to the length. The field lines will ripple perpendicular to their length, and they contract along its length, that is longitudinal. The field lines ripple perpendicular to its length and they contract along their length. This is another important point you have to understand regarding the magnetic field lines. Now we will move to an example from this one, that is example 5.6. So I request all of you to take your NCERT book and go through this question by pausing this video for a minute. Based on the knowledge that we had up to now, Tell me which all represent the magnetic field lines correctly, which all represent electrostatic field lines correctly. This is a question that I am giving you. Just find the answer and then proceed with the video. Now pause the video and find the answer by yourself. Which all may represent magnetic field lines correctly and electrostatic field lines correctly. Okay, I am discussing it. I am continuing with my class. Can option A represent magnetic field lines? As I told you before, this cannot represent magnetic field lines. This is wrong. Can this represent electrostatic field lines? Obviously it is possible, because electrostatic field lines can originate from a point. Magnetic field lines cannot originate from a point. Now coming on to this one, can this represent? Okay, this is absolutely no, because magnetostatic field lines, magnetic field lines as well as electrostatic field lines never intersect. Now coming on to the third one, this is all pretty clear as per the figure. This can represent magnetic field lines, because this is just like a toroid, the field inside a toroid. This is just like the field inside a toroid. So obviously this is possible. This is absolutely correct for magnetic field lines, but this cannot be the representation of electrostatic field lines. Let me tell you, this cannot represent electrostatic field lines. Okay, coming on to the fourth one. This is obviously correct. This represents, okay, E I am saying, not B. This is E. This will represent magnetic field lines, but cannot be electrostatic field lines. Now coming on to the point D, as we have already discussed, the field inside a solenoid cannot be likewise, because it has to be a part of a closed curve. It has to be a part of a closed curve. This cannot be your answer. Now coming on to this one, can this represent magnetic field lines? I think no, because if you look at this one, everything is originating from this one. Everything is originating from here and terminating here, and this cannot be possible with a magnetic field line. This cannot be possible with a magnetic field line, but it is possible with electrostatic field lines. Coming on to the last one, this is what I am saying, two pole pieces of a magnet. Okay, this is north pole and this is south pole. Can this be correct? I don't think so, because if you look at a north pole and if you look at a south pole, so one has to say, okay, these field lines are okay, and there should be some edge effect, otherwise what is called a fringing effect of the field lines. Fringing effect. This kind of effect is called a fringing effect. The same thing can also be seen with the capacitor. This is positive plate, this is negative plate. The field lines are likewise. And so here also field lines are possible with electrostatic field lines. And this kind of effect is called, the effect is what is called fringing effect or edge effect. Now let me tell you, so this cannot represent the magnetic field lines. So this is wrong. Which means among the four, one which represent the magnetostatic field lines are C and E only. I hope this example is clear to you. Moving on to the next thing, that is Gauss's law for magnetism. May I draw something like, okay, this is a bar magnet. This is a north pole and this is a south pole. Now I am constructing a closed surface called a Gaussian surface. So okay, fine. You will not agree with me that on the surface this is a what I am saying, a cuboid. This is of the shape of the cuboid. So how can you enclose by means of a sphere? Okay, I will construct another box for this purpose. And let us see whether this will work or not. Don't, okay, just a rough representation only. Don't say that it is symmetrical and asymmetrical. So it is coming out here. And it is entering here. Right? Now what you will say is that, sir, as many field lines which are leaving this surface will enter the other through the other surface also. My question, what is the total magnetic flux here going to be? Total magnetic flux. Magnetic flux, it means relative number of field lines intercepted by an area. What is the relative number of field lines intercepted by this box? The relative number of, or the number of field lines that I will specifically say. The number of field lines left this cross section or this cuboid is entering through the other one, right? So I can say total flux is flux left plus flux entering, or rather minus. Flux leaving minus flux entering is what is called the total flux, and let me tell you, this is equal to 0. Now according to Gauss's law, this can be written as closed integral. There we got E dot ds. Here I will write B dot ds, and you can see that for closed integral B dot ds is equal to 0. Closed integral B dot ds is equal to 0. So that is what the law says. The net magnetic flux through any closed surface is 0. Net magnetic flux through any closed surface is 0. This is Gauss's law for magnetism. Gauss's law for magnetism states the net magnetic flux through any closed surface is 0. Okay. That means this law can also be said like this. Magnetic monopoles does not exist. Every magnetic configuration has a north pole and south pole. Every magnetic configuration has a north pole and south pole. Whether it is a current carrying conductor, whether it is a circular coil, anything if you consider, every magnetic configuration has a north pole and south pole. Hope this much part is clear to you. Now we will move to another example. Example 5.7. Magnetic field line shows the direction at every point along which a small magnet is nearly aligns at that point. Do the magnetic field lines also represent the lines of force on a moving charged particle at every point? Now, if you just think about it, so far I never used the word magnetic lines of force. I never used the word magnetic lines of force. So far I use the word only this one, magnetic field lines. It is wrong to say magnetic lines of force because, as you know, this is the direction of magnetic field at a point. Now I am releasing a charge Q likewise. Now we know that the force experienced by the force experienced by the magnetic charge is perpendicular to the magnetic field. The force is perpendicular to the magnetic field. The force experienced by a charged particle is perpendicular to the magnetic field. Understand that clearly. Force experienced by a charged particle is perpendicular to the magnetic field, which means your answer is no. It's a big no, I will tell you. So answer to the first part A is no, because force is perpendicular to the magnetic field on a charged particle. Understand that clearly. The force experienced by a charged particle is perpendicular to the magnetic field. Now the second part. Magnetic field lines can be entirely confined within the core of a toroid, but not within a solenoid. Why? I told you, magnetic field lines have always formed closed loops. Magnetic field lines always form closed loops. So this can be enclosed by only that body which has no ends. This can be enclosed only by that body which has no endpoints. Perhaps a solenoid has ends, whereas a toroid does not have ends. Toroid does not have ends, whereas a solenoid has ends. Now, hope you got the answer. The answer I can summarize is toroid has no end points. Now coming on to the third point. If magnetic monopoles existed, how would the Gauss's law of magnetism be modified? Yes, magnetic monopoles existed. In that situation, closed integral B dot ds should be equal to. We know according to Gauss's law, closed integral E dot ds is equal to Q divided by epsilon 0. Now, analogous to 1 by epsilon 0, we have learned it as mu 0. Analogous to 1 by epsilon 0, we have learned mu 0. Now here, I will write Qm, where Qm is called a magnetic charge. Qm is just said as magnetic charge. It is magnetic charge. Now coming on to the point 4. Does a bar magnet exert a torque on itself due to its own field? We have the formula for torque. Torque, as we learned in the previous chapter, is M cross B. In this case, the B is nothing but external magnetic field. It is external magnetic field. Now the question. Here, in this case, does a bar magnet exert a torque on itself due to its own field? So, what is the external here? What is the value of the external field here? External field. How much is the external field? 0, which means torque is equal to 0. Does, now the next question, does one element of a current carrying wire exert a force on other element of the same wire? There is a possibility if they are parallel. Let me explain with the circular coil. Now if you look at the circular coil, it carries a current like this, this carries a current like this. Now you can see, taking a small element of this current and another element. We have already learned in the previous chapter that parallel currents attract, anti-parallel currents repel. Always this element will exert a repulsive force on this element, and this element will exert a repulsive force on that element, which means they will have always a tendency to repel each other. They will have the tendency to, their tendency is to repel each other, let me tell you. Now the next question, magnetic field lines arises due to. So the answer to the second part of the option D is yes, it's an absolute yes. Magnetic field arises due to charges in motion. Can a system have magnetic moment even though its net charge is 0? Answer is absolutely yes. If you look at this current carrying conductor, it carries a current although net charge is equal to 0, because we have learned that a current carrying conductor is electrically neutral. A current carrying conductor is electrically neutral. So let me tell you, it can have a magnetic moment. And the magnetic moment M is equal to, if the radius of this coil is R, I into pi r square. So answer to the last part is also a big yes. Answer to this part is a big yes. So please understand this point clearly. So the next topic that we are going to look at is bar magnet as an equivalent solenoid. Bar magnet as an equivalent solenoid. I am not going to discuss what is given in the NCERT book because it has given a lot of confusions, I tell you. This can be completed only in one sentence, I tell you. NCERT has given a lot of things, but I am not going to that kind of things because I will complete this in one sentence. I am saying. See how I am going to take it. Okay, let me consider a solenoid of certain length, say 2L, such that this length is L, this length is L. Now I want to find out the magnetic field at a point P, which is at a distance R from the center of this one. This is the radius of cross section of the solenoid. This is the length of the solenoid. So let me tell you the first point. Small r is much greater than L, and small r is much greater than capital R. This is an information given in the NCERT book, not made by me. But in their discussions they have made it so complicating that everyone feels this is a difficult thing. Now there are n number of terms in this solenoid, so small n is equal to capital N divided by 2L. So let me take a small element of length dx at a distance x from this one. Now this will feel like, or we have to say that, or we have to say that this resembles like a circular point. This is a circular point, and at a distance small r from the center. Then you will say, sir, it has to be r minus x. Sorry children, I will not take it as r minus x because compared to r, x is very small. Compared to r, x is very small because already L is very small. Now x is smaller than L, so I can simply write as r itself. So we will say this radius of cross section is r. dV is the magnetic field produced by this one. This is mu 0 divided by 4 pi into r cube into 2 into I into pi r square dn, where dn is the number of terms associated with this one. Now from here I can say dn is equal to n by 2l into dx. Right? So I will get this answer is equal to mu 0 by 4 pi r cube into 2I pi r square into dn can be replaced with the n by 2l into dx. N by 2l into dx, right? That is dv is equal to, that's going to be the value of dv. Okay, from here, what I am going to do is I am going to find the value of b. B is equal to mu 0 by 4 pi r cube into I into pi when I pi r square n is what is called magnetic momentum. I pi r square, I into a, that's a moment of one turn, and the solenoid has n turns means total magnetic momentum is equal to I into pi r square into n. So mu 0 by 4, mu 0 m by 4 pi r cube I can take, sorry, 2m by 4 pi r cube. Again another 2l at the denominator. Now integrating within the limits. This is, so first I will take first element here, last element here. So which means minus L to L dx. So we will get this answer as mu 0 by 4 pi small r cube into 2m in the, when you integrate this function, integral of dx is x within the limits minus L to L, the whole divided by 2L. Now what will get here? This is equal to, now this much part, I am so lazy that I am not going to write this part. Equal to. So what I will get is, if applying limits, this is L minus L divided by 2L. L minus L is 2L. 2L divided by 2L is gone. So which means you got the magnetic field B is equal to mu 0 divided by 4 pi into 2L by R. Now comparing this formula with what we have learned in electrostatics for a dipole. Electrostatics for a dipole, that is E is equal to 1 by 4 pi epsilon 0 2p by r2. That is the value of the axial line. This is a point on the axial line. Just like the way you have proved the required condition. You have proved the required condition, that is mu 0 by 4 pi into 2m by r cube. So this is the magnetic field at a point P on the axis of a short solenoid. Hope you understand every aspect of today's class. Study well. Thank you.